Good morning, my name is Megha Bhardwaj and today I'll be presenting upon the application guidelines for the ground fault protection system. In this presentation, I'll be mainly discussing about the comparison of the different type of ground fault methods based on the security, sensitivity, their advantages and disadvantages, the major challenges faced during the calculations, and application to improve the relay setting elements, and effect of inline switching on sensitive set ground fault detecting elements. So starting with the type of ground fault ground detection methods, first one we have is the directional zero sequence over current. Second is the directional negative sequence over current. Then the third is quadrilateral ground distance, and the fourth one is the Moho ground distance. Starting with the ground zero sequence over current, it can be calculated with the expression given here, that is IR is equals to IA plus IB plus IC. The couple of advantages of the zero sequence over current elements are they provide the outstanding resistive fault coverage, and they are easy to set and understand, and these are not affected by the load flow because the load current has very little impact on the zero sequence current magnitude, and these are also not affected by the face-to-face connected loads. Similarly, there are some disadvantages of the zero sequence over current, which are that these are affected by the changes in the power system sources, these are affected by the zero sequence mutual coupling, these are affected by the normal system load unbalances, and are also affected by inline switching open phase conductors. The next one is the negative sequence over current. This can be given with the expression shown here, and some of the advantages of the negative sequence current elements are that these are not affected by the inter-circuit mutual coupling, the problem that we have for the zero sequence. Therefore, for the remote and like long lines, negative sequence current elements provide better resistive fault coverage than the zero sequence current elements. Some more advantages of the negative sequence current elements are that these provide the outstanding resistive fault coverage, they have better resistive fault coverage than the zero sequence, and these are insensitive to the mutual coupling associated with the parallel transmission line applications, and these are not affected by the load flow because the load current has very little impact on the negative sequence current magnitude, and definitely these are preferred over the zero sequence over current elements. Also, if the bus is behind the relay location and the negative sequence voltage available at the relay location is higher than as compared to the zero sequence voltage. Some of the disadvantages of the negative sequence over current elements are that these are affected by the changes in the power system sources, these are affected by the normal system load unbalances, and also affected by the inline switching and open phase conductor with Next one, we'll discuss about the directional supervision of negative and zero sequence over current elements. This diagram shows the zero sequence phasors for the single phase to ground fault, and the expression defines the voltage and the current vectors for A phase to the ground fault. The torque equation is given below. Similarly, this diagram shows about the phase and the negative sequence phasors for the single phase to ground fault. These are all the impedance based calculations, and which provide a better operation for these conditions. Next one is the negative sequence directional element measures negative sequence impedance at the relay location. That is based on the impedance. The negative sequence function is based on the impedance calculation. For example, if the impedance is measured less than the forward impedance threshold setting, it will be known as the forward fault. Whereas if the negative sequence impedance is greater than the reverse impedance threshold setting, it will be named as the reverse. It will fall in the reverse. Here you can see in the diagram, it clearly indicates the reverse fault impedance measured and the forward fault impedance measured, based on which we decide the direction based on the impedance. Next one comes the quadrilateral ground distance. This one is a typically characteristic for the radial system, and it has the four elements, that is ZL, that is a transmission line impedance, ZR, that is a distance impedance reach, RF is a resistance C reach setting. 32Q is the directional element for defining the bottom of the characteristics. And another definition is the reactance elements are the topmost line, and the positive and the negative resistance boundaries are the right and left side, and the directional element that is the bottom line. So the impedance, whatever impedance falls within this correlator, the correlator ground distance characteristics operates if the measured impedance is inside the box defined by the 4 element. So if the measured impedance falls within this correlator, then that is defined as the measuring impedance. Also, the amount of the fault resistance covered by the correlator element is determined by the resistive reach setting, as we defined in the previous slide. And the correlator distance element is good choice for the protection of the underground cables. Also, the small zero sequence impedance angles makes it difficult to apply a Moho distance element for ground fault detection. So next comes that some advantages and disadvantages of the ground fault distance. Correlator ground distance, that is, it provides more fault resistance coverage than the Moho element. When properly designed, it provides high speed tripping of the resistive faults when a pilot channel is not present. These are fairly immune to inline load switching and are good for cable protection. Also, some of the disadvantages are that these are affected by the errors in the current and voltage measurements when the resistive reach is much greater than the reactive reach, and are also affected by the system non-homogeneity. That is, when the sources are unequal, source angle and the line impedance angles are unequal, and these are also affected by the zero sequence mutual coupling in the parallel lines. Next comes the Moho ground distance. Here you can see the diagram that ZL represents the transmission line impedance and ZR represents the distance element reach. So the Moho element characteristics are developed by measuring and comparing the phase angle between the operating voltage signal and the polarizing voltage signal. The positive sequence voltage polarized Moho characteristics provide the best security and dynamic expansion. Some of the advantages of the Moho distance are these are easy to set and are less influenced by the system non-homogeneity as compared to the correlator element, and these are capable of providing a better resistive fault coverage than the correlator element. Next is the disadvantages. They provide a limited resistive fault coverage for the faults at the end of the element reach, and provide limited resistive fault coverage for the strong source conditions, and are also influenced by the zero sequence mutual coupling. So these were some of the disadvantages of the Moho ground distance. Next we will be discussing about the difficulties associated with the ground fault protection. That is, the difficulties associated with the ground fault protection when we have when the system is non-homogeneous, that is, the source and the line impedance angles are not equal, and also the problems like zero sequence mutual coupling and the remote in feed into the high resistance faults, and the system unbalances due to the inline load switching or the line configuration. These difficulties are significantly reduce the ability of the ground fault protection to reliability and securely detect the high resistance ground fault. So these were some of the difficulties associated with the ground fault protection system, like non-homogeneity, zero sequence mutual coupling, and the remote high in feed high resistance faults. Again, this is to summarize the ground fault detection challenges, that is the system non-homogeneity, zero sequence mutual coupling, remote in feed into high resistance faults, and the system unbalances due to inline switching. Now, the effect of the non-homogeneous system on the reactance elements. So, as we earlier described, that the system is non-homogeneous when the source and the line impedance angles are not same, and that is the angle of the total current in the fault is different than the angle of the current measured at the relay. So the difference between the fault and the relay current angles can cause the ground fault distance relay to severely underreach or overreach. So this is the effect of a non-homogeneous system on the reactance elements, that it can cause the underreach or the overreach. Also, this diagram shows the voltage drop across the fault resistance for the non-homogeneous system, which includes both the real and the imaginary terms, the above one. So the imaginary part can cause the reactance element to overreach or underreach, and the reactance element error is defined. So the next conclusion is the reactive elements will underreach if the IF leads IR, as you can see in the diagram, and it will overreach if IF lags IR, whereas IR is the polarizing quantity for the reactance element. Also, we have the voltage vector diagram for the resistive fault in the homogeneous system and the radial system, just below for the non-homogeneous system diagram. Here you can see that the current and the current is in phase with the resistance, whereas it just has a real part, whereas in the non-homogeneous system it has imaginary and the real parts. Also, measuring negative sequence or zero sequence source impedances at the relay location. And the method 2 is the distance based measuring elements measure an apparent impedance to the fault based upon the ratio of the relay voltages and to the relay current. We'll be discussing about this in the upcoming slides. So and depending upon the as we discussed earlier, for the non-homogeneous system, the fault resistance induced error can be defined using this expression where RF is the actual fault resistance at the fault location, IR is the ground current measured by the relay, and A is the magnitude of the result in the above equation, T is the angle, I is the phase current measured at the relay for a vaulted fault, Z1L is the positive sequence line impedance, and K0 is the ground distance relay zero sequence compensation factor. So by calculating the zone 1 resistive reach, the amount of reactance element overreach caused by the fault resistance induced error is also reduced, and the polarizing reference can be corrected in the ground reactance calculation to prevent the overreach of zone 1 elements. So this is the compensation that we can do for the for correcting the elements. Next, we'll be discussing about the zero sequence mutual coupling, as we mentioned earlier. So zero sequence mutual coupling between the parallel circuits can cause a ground distance relay to overreach or underreach. It can also increase or decrease the voltage and the current measured at the relay, which affect the ground distance measurement. And the mutual coupling of the two circuits can cause a reduction in the zero sequence current in each line for the remote faults. So the correction for this is the direct tripping of the zero sequence overcurrent elements. And the next is the high resistance fault coverage and remote in feed. This is one of the next problem. So the amount of resistive fault coverage by any relay is influenced by the number of factors, that is a distance, element reach, directional sensitivity, remote in feed, line length, normal system imbalances, and the load flow. These all factors affect the high resistance fault coverage. Next is the system unbalances due to the line configuration or in-line load switching. So this affects the sensitivity of the zero and the negative sequence overcurrent elements. And now what is the next? So selecting the best ground fault detecting element. How can we select the best ground fault detecting element? Looking into these problems. So the zero sequence and the negative sequence overcurrent elements in the pilot scheme provides the best protection with respect to the security, dependability, and sensitivity. Also, using the combination of the zero and a negative sequence overcurrent elements provide the maximum fault resistance coverage for long and the short lines with and without mutual coupling. So the solution is to use both the zero sequence and negative sequence in combination to avoid all these problems. And hence the conclusion is that never set the ground fault protection elements more sensitive than the normal system unbalances due to the line asymmetry and unbalanced loading. Use combined zero sequence and negative sequence overcurrent elements in the pilot protection scheme to obtain the best high resistance fault coverage. Also use ground moho when the high resistance fault coverage is not a concern. The ground distance relay provide a good ground fault protection independent of the pilot protection scheme. And the quadrilateral ground elements can provide a good fault resistance coverage. Also, zero sequence mutual coupling can cause the ground distance elements to under or overreach under certain conditions. The effect of mutual coupling should be evaluated and considered when setting a ground distance elements. Also, in line load switching creates unbalances that can cause the sensitive overcurrent elements to operate and possibly trip. So the corrective action must be taken to block these elements during the switching operation. Thank you so much.